It's not gonna turn.
Okay? This is a closed pipe.
Can you see her?
Can you see?
Yes.
Okay. These two ends, when the pipe is open at both ends, are free to vibrate. So these are free ends. As free ends, they have maximum amplitude, so they act as antinodes. So if I look at the waveform, it's going to look like this, where I have an antinode at each end, a node in the center, and since I go and I reverse the letters, N-A-N, that's a loop. So this is one loop, so the length of the pipe is half a wavelength. All right? Now come over to here. This end is free. It has high amplitude, so you can think of antinodes as constructive interference and high amplitudes. This end is closed, so it is fixed. It can't move.
Wait.
So therefore, there's no movement, okay? So now what we have is only half a loop. So therefore, now the length is 1/4 of a wavelength. Okay? Now, we share the same wave speed because they were done in the same room. Yes? So they have the same wave speed. And remember, wave speed is frequency times wavelength. Yes?
Yep.
So for the wave speed, VW equals F times the wavelength, and this wavelength would be 2L. Does that make sense? So therefore, the frequency you heard was the frequency generated by a particular wave speed with a wavelength of twice the length of the pipe, and that was the frequency heard. Now come over here. Wave speed equals frequency times 4L. Yes?
Yeah.
So that means that wave speed divided by 4L is the frequency. Therefore, this frequency is half as big as that one. Yes? Because this I could rewrite this as 1/2 of VW over 2L.
And you can see that in the beginning, right? When L equals 1/2 lambda, and then the other one is L
Yes.
equals 1/4.
Okay, but that change in wavelength, the frequency is exactly the opposite. So if the wavelength gets 2 times bigger, the frequency gets half as big. Yes?
it's slower.
Okay, so now, we're going to do it once more. I would like you to choose 2 pipes that look like they're in a ratio of about 1:2. The other one's about half of it. So put yours over here and see if we can find 2 pipes
Here,
that look
Alan,
like we
I think
sort of
we're gonna
have.
need one of, this looks about like half. Here. 6 and 17.
Okay, those look like half. Put them next to each other. What do you think, Sarah?
Yeah.
Looks reasonable. Okay, so somebody played the, okay, now wait a minute, we're going to do it right now. This would be the lowest frequency because it has the longest wavelength. This would be a higher frequency because it has a shorter wavelength. Yes? When this is closed, this wavelength is cut in half, right? So the frequency is even lower. And when this is closed, the frequency is even lower. Yes? Okay, so we're going to do open, open,
Close, close.
closed, closed.
Okay.
And see if we can hear it. Okay?
So open.
So you want open, then open on the other one, then closed on the, I think. Let's see what happens.
We good facing this way?
Yeah, I don't care how you face. All
Okay.
right, let's just see if you hear it. Now, play yours closed. Okay, now let's try to do it faster, okay? Open.
Almost.
Did that work? Because I don't have good ears.
Right.
Okay, so
I
what
want
do
it to
we,
go
what do we want
from-
to hear?
Okay, we want to hear the frequencies generally declining.
And so it'll be this, 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 this. Like me, Sarah, Sarah. me.
Shortest
Wait, this
wavelength.
closed-
No,
This one
her.
being
Oh,
closed is going
'cause
to be
these are-
equal to this one
Yeah,
open.
these are.
That's what I
an
think.
octave or-
So,
they're
Yeah.
the same
so you
note.
want to do open, close, right?
Yes. So tell them what to do.
Tell us what to do. No, open, close.
So
close,
this
open,
is the
right?
highest frequency.
Yeah, so it goes. And then
I'll come in. at
Wait,
the
so
same
you're trying to go high,
High frequency to lowest frequency.
Okay,
Oh,
so that's
then
gonna
I
be
said-
you open.
open, close?
Then you open, then you close.
All right, now, according to Alan and in my brain too, your open should be
My
her
close.
closed.
If we did it at the same time, would it harmonize?
I don't know.
No, 'cause it's
So,
standing up, right?
let's see.
Wait,
No,
am I open?
You,
Does that sound close?
Hers is louder.
Hers is
Yeah.
louder. Okay. That's pretty close, isn't it?
Yeah.
I mean, I can't tell because I can't hear, all right? So, but if we fit our ratio of halves and wholes, right, then this one doubled in, this wavelength doubled, right? And that's what the length of this tube is. Yes? Okay, if you can find two others, maybe you can hear it better, I don't know. Maybe if she gets to use a shorter one, can you use shorter ones that are half? Maybe the length of it's too hard.
Shortest.
I think probably number one.
Yes.
these ones I
I would
think
assume
are
so. Oh, here, okay. That's like a little, yeah, okay.
Oh, this is one.
I see. That's longer, yeah. Okay. Okay.
Okay, what number do you have in this hand?
Ooh, 12?
Here's 13. Is that any better to match?
That probably is.
Yeah, that one
Yeah.
is better.
Okay, all right.
That's pretty close.
It's pretty close.
Yeah,
So it's what's happening is we're getting an overtone in there. That's why you get that other one higher. But the concept is you can change the frequency of a pipe by deciding whether it's open or closed. Is that good? Okay, now, if your frequencies are not identical, oh, I gotta have her stand. I'm sorry, I need the stand. If the frequencies are not identical, then what you hear is something called a beat. And that's the way orchestras tune, is they all play the same note. Yes, ma'am?
How do you, oh, like, oh, no, I'll ask you.
That's okay, all right. Now, these two are supposed to be 256, they're both supposed to be the same, but they're not, all right? So this is one manufacturer's 256, ha-ha. Another manufacturer's 256, ha-ha. They don't match, all right? Now, these are called sounding boxes, which make the sound louder, all right? Because instead of just vibrating
Do you want a shoe?
the,
She has a mallet.
Oh.
It's really
instead of just
beneficial.
vibrating
Okay.
the
That's your best.
air that's near the fork, it also vibrates the air inside the box, all right? Now, if we take this tuning fork and I just hit it, you can hear, yes?
Mm-hmm.
Now, if I hit it,
It's vibrating the table.
now it's vibrating the table. And because it's vibrating the table, you can hear it that much better, right? So the vibration now, by hitting the table, that means this is going to damp out sooner. And the word damp means lose energy too.
Like
all right?
dampeners during
So
an
this
earthquake.
is, if I hit it like this, it might ring. Can you see the times? Here.
Oh, yeah, I can see it. Messes with my eyes kind of, but.
Can you see them vibrating?
Mm-hmm.
In and out and in and out.
Like
Oh
really
my God,
small.
talk about craziness. All right. But it'll vibrate longer this way because the energy it has to put in is the energy to the air than it would if it vibrated this way. All right. So this will shorten it because it has to also move the air over the table. All right. So sounding boxes.
Wait, so
These-
why is it shortened?
Because it now is also having to vibrate the entire mass of the top of the table.
Okay, so it's just putting
And
more energy
It's
out.
putting more energy out, and therefore the air mass and the table are going to shorten how much energy I gave it.
Okay.
All right? So now, these are supposed to be the same. Can you hear the beat?
Mm-hmm.
Yes?
You can hear it better on that one.
Yeah, this is the right frequency. All right? So here is a legitimate frequency. Okay? If this was the same frequency, then they should blend and just give you a huge amount of constructive interference.
Oh,
Okay.
so what? Because when they're both on, you hear the like.
This one might be